All right, so I've got a couple of questions here that we can use to think about the rank equation and just in general about the dimension of the row space and null space and how those relate. So let's say that we have a 4 by 3 matrix. What is the maximum possible dimension of the row space? So remember that the dimension of the row space, this is equal to the rank of the matrix, which is equal to the number of pivots in that matrix. Okay, so what's the maximum number of pivots we could have in a 4 by 3 matrix then? That's really the question. So if we have 1, 2, 3, 4 rows and 3 columns, then the maximum number of pivots would be 3. If we have, let's say, pivots going down the diagonal here, we're going to run out of columns at 3 columns. So that's our maximum possible dimension of the row space. It's 3. At most, 3 of these rows could have a pivot in them. And so another way of thinking about that, that's the maximum possible rank of the matrix would be 3. If A is a 4 by 6 matrix now, so still 4 rows, but now let's say it has 3 more columns added to this, what is the smallest possible dimension of the null space? Okay, so dimension of the null space. Remember that you get a basis for the null space based on the non-pivot columns. Those end up being your parameters, if you think of it in terms of the solution set to the homogeneous equation AX equals 0. So anyway, the dimension of the null space is going to equal the number of non-pivot columns. So the rank is equal to the number of pivot columns. The dimension of the null space is equal to the number of non-pivot columns. And so like I said, for a 4 by 6 matrix, let me use the drawing that I had up here. I'll have to get rid of this. So now we're going with 4 by 6. So we've got 3 columns. I need to add 3 more. 1, 2, 3. So now, and sorry, let me write one more thing for us to refer to, and then we'll start to analyze this. The rank equation. So rank equation says that the rank of a matrix A, which is equal to the number of pivot columns, plus the dimension of the null space, which is equal to the number of non-pivot columns, dimension of the null space, will equal the total number of columns. That makes sense. This is the number of pivot columns. This is the number of non-pivot columns. So this equals your total number of columns. Just your number of columns overall. I'm going to write it this way. So if we want the smallest possible dimension for the null space here, then that means that we want the maximum possible value for the rank. We want to leave as few non-pivot columns as we can. So we're trying to get a pivot in as many columns as we can. So you go down the diagonal like that. So the smallest possible number of non-pivot columns would be 2. Best case scenario, we end up with a pivot in all 4 rows, which means pivot in 4 columns, and then we have 2 left for the dimension of the null space. Okay, so our smallest possible dimension for the null space of A here, the answer to question B is 2.